Right. So yeah, thanks very much for the invitation. So I'm going to talk about the diagonal of quartic fivefolds joined with nib Pavich. And okay, so let me start with a definition. So throughout X will be a variety over a field K. And I'll be interested in retract rationality. So X is retract rational if and only if there are rational maps F and G that fit into the following diagram. So you regard the identity on X as a rational map, and then as a rational map, this should factor through projective space like this. So F and G are rational maps, and N is an arbitrary integer, but since the composition is the identity, it's dominant. So N has to be at least a dimension of X. And a simple example, so when does this happen? So if you multiply X with some other variety, and if this is rational, then X is retract rational. And why is that? Well, if this thing here is rational, it's birational to Pn. Everything in this diagram are rational maps, so you can replace Pn by this X times Y, and then F is the inclusion of a factor and G is the projection. So in particular, if here Y can be taken to be a projective space, then one says that X is stably rational. And so in particular, stably rationality implies this retract rationality. So rationality implies stable rationality implies retract rationality. And this implies unirationality, simply because this map here has to be dominant. So there is dominant map from Pn. And right, so here the opposite is not true. And this is also not true. And here we don't know. Okay, so this is this famous example of a threefold that is stably rational, but not rational due to Coulomb, Bouville, Son-Suk, and Sonnet-Dyer, and this is the Artin-Mumford example. Okay, so one class of varieties where one can try to see where in this list of implications the variety sits are hypersurfaces. And so I quickly say over C of degree D, and let's assume that it's very general. All right, and then there are some classical results on this, maybe to spend. Most of you know this very well. So yeah, so cubic threefolds are not rational by Clemens-Griffith, and then quartic of D is 4 and N is 3. This has been done by Iskowski-Manin. They proved that these hypersurfaces are not rational. And then Colliot-Delaine and Perutka much later proved that they are not stably rational. In fact, not retract rational. And then still degree 4, but now dimension 4 has been done by Totaro. And again, he can prove that they are not retract rational. And Totaro has a linear bound that improved the linear bound of color, and an improvement of this due to myself that says that if D is bigger or equal than the log 2 of the dimension of n plus 2, the dimension is at least 3, then X is not retract rational. All right, so what happens if one puts n equals 5 here in this formula, then one gets d bigger or equal 5. And the motivation for the talk that I give today is a theorem of Nikese and Ottom, who can improve this bound here. So they show that if X in P6 over C is a very general quartic, then X is not stably rational. Okay, and the point here is that these previous approaches, they all detected, in fact, not only stable rationality, but retract rationality. And so far, nobody really cared, because all these approaches that would detect stable rationality, in fact, detected this one. But there's a new approach that does, in fact, not detect retract rationality, but really only stable rationality. And Nikese Ottom used that approach. So they cannot, with their approach, they cannot get retract rationality. And since there is this approach that really is sensible to this stable rationality, it is a possibility that one can use that approach to prove that, well, to answer this question, to find something that is retract rational but not stably rational. So this is the motivation of this talk, and more concretely, we ask whether this quartic is retract rational or not. Well, that's one motivation. Another motivation is, so remark, so their approach does not work for retract rationality or in positive characteristic. So another motivation is to see whether one can get this over other fields, over positive characteristic fields. Okay, so before I explain the answer that we found with NAP, I want to recall how Nikese and Ottom proved this theorem. I already mentioned that they are using an obstruction that is really sensible to stable rationality and not retract rationality. And this is the motivic obstruction of Nikese, Schinder, and Kontsevich-Cinque. So let me briefly remind you what that said. So if X, say, over the power series ring in one variable over C is strictly semi-stable, that means the total space is regular and the special fiber is a normal crossing divisor. So locally looks like the intersection of hyperplanes. And all the components are smooth. So if you have such a nice degeneration with special fiber, Y that has some components, then the geometric generic fiber, if that is stably rational, then there's a certain identity. A certain identity holds in the free abelian group of stable birational equivalence classes. Where this one here is the intersection. So for a subset of the index, so big I is the index set of the components, And for any subset, you can intersect the corresponding components, you get some strata. And we sum up these strata with some coefficients. And this has to be the same in the free abelian group of stable birational equivalents if I select a point, if the geometric generic fiber was stably rational. So if you find some semi-stable degeneration of your variety you're interested in that does not satisfy this equation in this very simple ring, then the generic fiber was not stably rational. But it does not follow. So this uses big factorization. So resolution of singularities very heavily. So it doesn't at the moment not work in positive characteristic, though we expect it should if resolution of singularities holds. And more importantly, the method cannot or does not work for retract rationality. So it's really special for stable rationality. And now let me recall what Nikis and Otten do is they just write down a semi-stable degeneration of quartics where this equality is not satisfied, and then they're done. So let me prove. Proof of the Nikes-Otten theorem. Well, you have to find a nice degeneration, and the one they use is the following. So it's given by two equations in a weighted projective space. Over this power series ring. It's a weighted projective space. There are 7 variables that have weight 1. So this is set 0 to set 6. And then there's one variable of weight 2. This is the W. And F is a quartic equation. So F is a quartic, homogeneous quartic polynomial that is very general, subject to invariance. Sorry.
And what is T?
Sorry. What is what?
What is T?
Yeah, so T is an element in this ring.
Ah, so it's the deformation parameter, right?
Exactly. Yes.
Okay.
So everything happens over this space ring, and for T equals 0, we get the special fiber, and if T is invertible, we get the generic fiber. And they assume that this quartic is symmetric in set 5 and set 6, but sufficiently general otherwise. Yeah, so there are variants of this. So you can write several variants. I use this one, and then I explain what happens. So the special fiber, I always call the special fiber by Y. What do we get? So T is 0. So we get set 5, set 6, sorry, the product. So this is a union of two hyperplanes, and then the second equation is a double cover like this. So this will be a union Y1, union Y2, where this Yi is a 2-to-1 cover of P. 5 branched at the quartic F, where, well, set 5 or set 6 is 0, but the symmetry by set 5 and set 6 tell me that it's always branched at the same thing. So set 1, Y1 and Y2 are isomorphic to each other. And Y1 intersected with Y2 will just be given by set 5 equals set 6 and this other thing. So if I call this set, then set is a 2-to-1 cover of P4 branched at the degree 4 equation that is given when we set Z5 and Z6. Sorry. So. Okay, so what about the generic fiber? Well, the generic fiber, we can invert T. So W will be, we can solve here for W, and W will just be this expression. And if we plug it in here, we get that it's just a quartic in P6.
T to the power -2, right?
Probably, yes. Exactly. Okay, so this is an interesting degeneration. So the generic fiber is a hypersurface, and the special fiber, maybe I emphasize this. So the special fiber has two components, Y1 and Y2, and the intersection Z is this 2-to-1 cover of P4.
And is the general fiber smooth?
The general fiber is smooth, and the total space is not regular, but you need to blow up a little bit. So this has very mild singularities, and I neglect this here. So if you blow, you can do a small resolution of the total space, and that does not change the components or their birational type. So it does not introduce new components. But you see here, this equation here has well, yeah. One can check that this has some very mild singularities that one should resolve. But there are small resolutions of these things, and I neglect them here. But the generic fiber, yes, this is smooth because F was just a polynomial in Z1 to Z6 up to the symmetry. It's completely general. So if I add this monomial to it or subtract it, it's still a very general polynomial, symmetric in Z5 and Z6, and this gives a very general hypersurface of degree 4 in P6 up to the symmetry in Z5 and Z6. Okay, so why do they insist on this on the symmetry? So we need to check the following thing. So the formula says that the sum of the components minus the intersection, we need to check if this is the same as the class of a point in this free abelian group of stable birational equivalence classes. But now this is not the class of a point. So this set is not stable rational by work of Hasid, Perutka, and Schinkel. That's the key point. So this is not a point, but these two things, they are the same. So I can write because they are isomorphic. So this is 2 times y1. But we are in a free abelian group, and then this cannot happen. So one way of seeing this is that we can reduce modulo 2. Then we are in a vector space over F2, and in this vector space, this goes away, and we would get that the class of Z is the same as the class of a point, but it's not true by Hasid, Perutka, Schinkel. So this is not true. And this proves the Nikese-Otten.
So you need to, so you first reduce and then apply Hasid, Perutka, Schinkel, right?
No. So I need to prove that this does not hold.
Yeah.
And one way of, so what you mean with reduce mod 2 or?
Yeah, so do you use something like Hasid, Perutka, Schinkel over?
No. So this is
just an argument about a free abelian group?
Absolutely. Yeah. So this is a very stupid argument. just in such a free abelian group, there's no way that you can find a class y1. So there's 2 times y1 minus z would be the class of a point, because z is not the class of a point. And one way of seeing this is that if such an identity would be true, I can tensor everything with z mod 2, just in this free abelian group, and this would go away. And then I would see that in the free abelian group over z mod 2 that is generated by stable birational equivalence classes, the class of z would be the class of a point. But that means that they are the same because it's a free abelian group or a vector space, right, over Z2. Is that convincing?
Yeah, I think possibly it's fine. Yeah.
Yes. So that they have the symmetry to get rid of this. There is another argument. So alternatively, we can make y1 and y2 singular. In fact, put a triple point there, and then they are rational. So okay, so this technically speaking, this makes more trouble, because then one has to, in the semi-stable reduction, one has to blow up the triple point and so on. So I don't want to show this here, but one can do that, and the new components that you introduced, they don't really mess up. In any case, so what I want to say is that one can get into such a situation where the 2 components are in fact rational, and then it would even be easier to see that this does not happen, because then this is the class of a point, that's the class of a point. You can cross out 1 point and you would get that this class is the class of a point. Okay, so the question is, the first question, if we have a quartic in P6, is it retract rational? Okay, and if it is, then it's probably, at least for me, impossible to find such a factorization of the identities. The only hope is that maybe it's not, and then we can prove that. But if we want to prove that, then the second question comes up is how to replace the motivic obstruction of Nikese-Schindler and Kontsevich-Zinkel in the above argument. I mean, this result of Kontsevich-Zinkel and, sorry, of Nikese-Schindler, Kontsevich-Zinkel is very, very central here, and one needs a replacement for this. So what I'm saying is that I want to use the same a similar degeneration. So I want to use a similar degeneration as they are using. So one has 2 components, and this intersection is stably, or it has no decomposition of the diagonal. It is non-retract rational by work of Hasid-Perutka-Zinkel. So I want to use such a degeneration, but then I would like to conclude, or like to see whether this implies something about the generic fiber. And the known methods that we have for this problem don't work. So one has to do something new here.
Yes. And so what does the argument of Nikese-Sotom so prove? So apparently they prove that like a 5-dimensional quartic is not stably rational, but does it also prove higher dimensions by induction?
No.
What happens if we apply it to a 6-dimensional quartic?
Yes, then you would need to know that double covers of P5 branched along a quartic are stably irrational, and we don't know.
Branched in a 5-dimensional quartic, right?
Yes. Sorry. Yeah. So roughly speaking, what Nikese, so this is a very nice and super clever degeneration. And what they managed to do is they managed to squeeze out more from the Sasset-Rutger-Jinkel example, because that example, you know, in dimension 4 we have this totaric result that quartic fourfolds are not rational, but the Hasse-Perutka result is much better because it says that it's better because double covers of P4 branched along a quartic, they are somehow closer to being rational.
I see. So yeah, I see.
Yeah. So there is no
They
way
have
of
a bigger index, right?
No, the index is the same, I think.
No, Fun index is bigger for the double covering.
Fun index is the same. This generation of one the same. In dimension 3, both have index 1, for instance.
No, in dimension 3, quartic.
Oh, sorry. I'm totally confused. Which double cover is this? It's a double cover of projective space branched in a quartic, right?
yes.
Yeah. Sorry, the index is bigger. Yeah.
I mean, the way I think about this is that it's an equation of this form, and this is a very special degree 4 equation, right? So if you dehomogenize it, it's just a special degree 4 equation. So this is, yeah. And in higher dimensions, to do an inductive argument, you would need to prove something for these special equations, and not for a general quartic. So there is no inductive way that one could go on. At least not an obvious one. Okay. So
And maybe
yes.
just one last question.
Yeah.
So Hasse-Perutka-Jinkel, they also need some generality condition anyway, right?
Right.
But
But that is all fine. So in this construction, F was very general. Only there was not only the symmetry condition, but for instance, you have no condition whatsoever. What happens if you put Z5 and Z6 being 0? So this restriction is really a general quartic equation. So this is a very general 2-to-1 cover of P4 branched at a very general quartic degree 4 equation. Yeah. Okay. Maybe one more thing that one should say is that in case in Autumn don't only have this very nice degeneration, but they also have a conceptual way of thinking of them in terms of tropical geometry, and that's how they can do complete intersections in large dimensions. And that's a conceptual way how you get these degenerations. In low dimensions, you can just write them down, but the larger dimensional examples they have, you can't easily write them down. However, for hypersurfaces, this is the only new example, and there we can do things by hand. Okay, so back to my question. I want to use a degeneration like this, or maybe a similar one, and want to see whether this does obstruct retract rationality. And for this, I need some kind of replacement of this Schreieder Kontsevich-Jinkel result. And so right. So let me start out very simple. So how do we obstruct retract rationality? And this, in fact, also explains why this is a very natural notion. If you see it for the first time, you might think this is strange, but it's very natural. So assume that you have a functor from smooth projective K varieties to abelian groups, which is functorial for rational maps. So either contravariant or covariantly functorial for rational maps. One of the two, doesn't matter. Then we have the following lemma. If X is retract rational, and this functor evaluated on projective space is 0 for all n, then f of X is also 0. So any functor that is functorial for rational maps and trivial on projective space gives an obstruction for a variety to be retract rational. And the proof is obvious. So we have this diagram. And then we apply the functor. And since we assume that the functor is functorial for rational maps, we get that the identity factors through this one. And so the identity factors through 0, because I also assumed that the functor is trivial on Pn. And so that group must be the trivial group. So this is certainly the motivation for, or one motivation for the notion of being retract rational, that it's a very natural source where such functors can be used to detect it. So what are examples? So the first example is you can just take differential forms of positive degree, so that certainly vanishes on Pn, and it is functorial for rational maps, because if you have a rational map, you get pullbacks, so it's contravariantly functorial, you get pullbacks on rational forms. So unramified cohomology would also be an example, but I don't want to talk about this today. Another example is the Chow group of 0 cycles, and this is because on a smooth projective variety, you can move them all, the 0 cycles always in general position. And if they are in general position, then you can pull them back with a rational map, because you can assume that they are supported where the map is actually defined. Now, the group of 0 cycles, so it is functorial for rational.
Sorry, probably you need to push forward, because the pullback of a 0 cycle is not a 0 cycle, right? The dimension.
I'm sorry. Yes. But what I meant, yes. But what I meant is, so you need to move the point so that the map is defined. Yes. And then you can push it forward. Absolutely. Yes. So here it's contravariant. And here it's covariant. But now this example, it is functorial, but it does not satisfy this one, obviously. So we can easily get rid of this by just looking at the kernel of the degree map. Then now this invariant also satisfies this condition. And the third example is the observation that whenever we have a field extension, then we get a new functor just by applying the old one to the base change. For instance, the kernel of the degree map. Okay, and so this so what turns out is that for smooth projective varieties.
Sorry.
Yes.
So your functor f should be then defined on varieties over L?
No, over K.
So
yes. This one, yes, that's right. Yes. The f is, for instance, this one. Yeah.
Yeah. So you extend scalars and then restrict them back. Right? So here, XL, do you consider it as a K variety?
Well, it doesn't matter really, but no, I think as an L variety, but for these, it only depends on the scheme structure, not on the.
So this is not for an arbitrary functor, but for the functor from example 2. Yes. Okay.
But you can do, of course, if you have some functor, you can do something similar. I think what you said is absolutely right. So you need a functor for varieties over L, and then you can do this business. But these examples, they are well behaved and they're doing extension of scalars.
Okay.
Okay, so if you like, I can replace this. I can remove it. So just this. I mean, we could do the same thing for the first example. but we wouldn't get anything interesting because the space of forms doesn't change. But this kernel can change. That's why this is really interesting. Okay, and so this observation leads to definitions that you probably all have heard before. So the first one is that X is universally CH not trivial, essentially if this third example is always 0 on X. And it's slightly stronger, so if the degree map is an isomorphism for all field extensions. And another definition is that there is a decomposition of the diagonal of X if there is a 0 cycle on X such that the 0 cycle of the diagonal is the same as the base change of Z. This is now this happens in the base change of X to the function field. And here, this is the class of the diagonal. So I draw a picture. We have X times X, the projection down to X. And here's the generic point and the generic fiber. And on X times X, there are two cycles. So there's a diagonal and a section given by Z times X. And now this diagonal class is this cycle. And this class is that cycle. And the decomposition of the diagonal exists if these two 0 cycles are the same. And okay, so that means also something about the global cycles on X times X by the localization formula. But the convenient way of stating is like this. And if I state it like that, then you also see that if something is universally CH not trivial, then that must be true if X is smooth projective, because this cycle has degree 1 and that cycle has also degree 1. They have both the same degree, and so the difference must be 0 if the variety is CH not universally trivial. So this is really a special case where one finds two more or less canonical cycles of degree 1 that have to be 0 if this universally trivial condition here is satisfied. And then there is a lemma that says that in fact, if X is smooth projective, then the two notions are in fact equivalent.
But how do you know that X has a 0 cycle of degree 1?
Yes. I need to assume this, yes. Okay, so now let me think. No, so well, no. What do you mean? I mean here. It's contained. It's a condition. It's contained in both conditions. So here I ask that for every L over K, the degree map is an isomorphism. So there must be a 0 cycle of degree 1.
Okay.
And
yeah.
here I'm asking for a 0 cycle on X with this condition, but that cycle has degree 1, so
Yeah,
Z
sure.
has to have degree 1. Okay, so no, so sometimes I make that mistake, but I think if I formulate it like that, then I don't.
Yeah, sure.
So if X is smooth projective, then the two notions are the same. X is universally CH not trivial if and only if there's a decomposition of the diagonal. It's more like a remark that, yeah. But that also explains somehow the title. So, but what I would like to know is whether the quartic has a decomposition of the diagonal or equivalently, whether it's universally CH not trivial. And if it is not, then this functor is not trivial on this X. And then by the lemma, X was not retract rational. Okay. So upshot of this is that if X is not universally CH not trivial or equivalently has no decomposition of the diagonal, then X is not retract rational. And yeah. So I would like to use this criterion. Okay, so now back to the Nicese-Occam degeneration. So what's our problem? So we have a semi-stable degeneration. Special fiber has two components. The intersection is integral. And for simplicity, I want to assume that these two guys here, the two components are rational, and Z is not CH not universally trivial. So yeah, so this is okay by Hasid-Peroutka-Zinkel. And I briefly mentioned before that it's more or less also okay. One can somehow reduce to the case where the components are rational. And even if they are smooth, we don't know whether they are rational or not. So let's assume they are rational and try to see what we can get from them there. So this will be somehow a simplification that I want to make now to think about the problem. Okay, so the special fiber has two rational components. The intersection is irrational. It has smaller dimensions, and Nicese-Occam are able to use the motivic approach to deduce from this lower dimensional irrational strata the irrationality of a higher dimensional generic fiber. Now, I would like to see whether one can detect how big the group of zero cycles of the generic fiber is. So I would like to say that the group of zero cycles of X must be big, if something like that happens. But now you see, if Y1 and Y2 are rational and everything happens over an algebraically closed field, then this Y, you can, after every field extension, the Chow group of zero cycles of Y is just trivial. Yes, so I can. So Y is CH not universally trivial. And so we are not happy. I don't know what to do. So the first idea is that somehow the problem is that the interesting information lies in Z, but Z is a divisor on this Y. It's codimension 1, and so it does not influence the zero cycles at all. So maybe we should blow up Z. So the first idea is 2-to-1 base change plus blow up Z, and then we get a special fiber. Well, now three components, the Y1 that we had before, and the Y2 we had before, and there's a new component, and this is a P1 bundle over Z.
Sorry, and why do we need a base change?
Otherwise, it's not strictly semi-stable. So if you blow up the yes, so if you blow up the single locus of the special fiber and don't do a base change, then the exceptional divisor will have multiplicity 2. And that's not allowed in a strictly semi-stable degeneration. So in a strictly semi-stable degeneration, the components of the special fiber all have multiplicity 1. But if you do a 2-to-1 base change, then the singular locus becomes singular of the total space. And if you resolve it, then you introduce a new component in the special fiber that has now multiplicity 1, and the total space becomes regular. So that's why the base change is necessary. Okay, so let's do a base change. Then we have three components. 2 are unchanged, so they are still rational. And this here, the middle guy is a P1 bundle over Z, but Z did not have a decomposition of the diagonal. And this is, or not, was not CH not universally trivial. And this is a stable birational invariant. And so also this P1 bundle over Z still has no decomposition of the diagonal. So this is not universally CH not trivial, or has no decomposition of the diagonal, as you want to say. Okay, so that maybe that is better, because now at least we have a whole component where zero cycles can live. But it's still not quite good enough. So here's the following example. So start with projective space over this power series ring and blow up So let's start with the constant family over the power series ring, and then we blow up a general okay, sorry, I'm a little bit confused. Okay, so my example goes like this. So blow up a general, say, codimension 2 subvariety. Then
codimension 2 in the fiber? In
the special fiber.
Codimension in the fiber, right?
Yes, exactly. So then we get, and then followed by blow up of point on exceptional divisor. And then what we get is this. So the generic fiber will still be Pn, and it degenerates to something that has 3 components. Let's see what are the components. So one component is the blow up of Pn and Z. The other is a P, okay, I took codimension 2, so it's a P2 bundle over Z. And in fact, the blow up of this thing, because in the last step, I blew up a point on this P2 bundle. So blow up of it. And this last exceptional divisor is a Pn. And now you see we are exactly in the same situation as before. So this is rational, and the guy in the middle has no decomposition of the diagonal. But yeah, this is rational. And that one is also rational. Okay, so this is an issue. So one has to look somehow closer. So what I'm saying is that we would like to use this Nicaise-Autumn degeneration, but what do we know about the degeneration? Let's assume that y1 and y2 are rational, and then all we can get is we can get such a degeneration where we have three components, and the component in the middle is not universally CH not trivial. But one has to use quite fine knowledge about this degeneration, because just the fact that there are three components ordered like that and being rational without a decomposition of the diagonal and rational is not enough, as this simple example shows. Okay, and now while writing down that example, I'm a bit puzzled about what I want to do now. Okay. Okay, so sorry that Jared, I prepared something, but I think there is an issue. So let me skip that what I prepared. I'm confused now. So let me directly go to the obstruction. Okay, the one that we use that should detect, well, an obstruction which on this special fiber is non-trivial, but is trivial on such special fiber. And in fact, it should be an obstruction for retract rationality or decomposition of the diagonal of the generic fiber. And of course, in this example, the generic fiber is just Pn. So our obstruction has to be zero on such degenerations, but we would hope for one that is non-zero on such a degeneration. Okay, no, this is already a bad start. So this is strictly semi-stable, but R is an arbitrary DVR with residue field little k algebraically closed. That's the setup. Okay, and then we look at the map. So as before, the special fiber is Y, and I denote its components by Y lower I. And what I would like to write down is a map that starts, okay, so this is incorrect. I would like to write down a map that starts with a 1 cycle on Y and spits out a 0 cycle on each component of Y. And there is an easy way of doing this. So if we have a 1 cycle on Y, this special fiber sits inside the total space. So we can push it forward, and then we have a 1 cycle on the total space. But each component of the special fiber is a Cartier divisor, so we can restrict this 1 cycle to the Cartier divisor and get a 0 cycle. So we get a map like that. So we have a 1 cycle in the special fiber, push it forward, restrict it to a component, get a 0 cycle. And now the fact that the whole special fiber has trivial normal bundle, you can move it away from the special fiber, easily implies that if you sum up the degrees of all these classes, then in fact you get 0. So in other words, this will sit actually in the kernel of the degree map to set. And now here's our result. So Pavic and myself. So first, assume that the generic fiber is universally CH not trivial or equivalently has a decomposition of the diagonal. Then for any unramified extension of discrete valuation rings. So okay, so what's an unramified extension of a discrete valuation ring? Think about the case where R is just a power series ring over C. Then for any extension of C, you just write down the new power series ring over that bigger field. So that's a typical unramified extension of DVRs. A ramified extension would be one where T goes to T squared or something like that. So example, take an extension of the take an extension of C and look at this extension. That's a typical unramified extension of DVRs. And for any such extension, we can base change the whole situation to A. And then we get a new family, now not over R, but over A. And this map still exists. And the statement is that whenever you do such a base change, that map is always surjective. So in other words, to retract rationality or a decomposition of the diagonal of X ether, it would be enough to find a special fiber so that this map here is not surjective after some base change. And the point is that this map, the way I wrote it down, it depends on the total space. But the point is that it in fact does not depend on the total space. It only depends on the special fiber. So this is really an abstraction where you only have to look at the special fiber and how the components intersect. And why is this? So this thing is easy to understand. So if gamma has support on a single white J, then we can compute this easily. So either it's just given by you intersect the one cycle with white J. If with white J intersect with yi. So white J is another component. So if I is different from J. Fi. So if you have a component, if you are at a component and the cycle has support on another component, then how do you intersect? Well, you do the obvious intersection, right? And this has only to do that, you don't need to know the total space. You only need to know the way these special fiber, the components of the special fiber meet. And now what happens if the curve, if you want to restrict the one cycle to a component that contains the one cycle, well, then it doesn't work that well. But then what you notice is that that component is rationally equivalent to the negative of all the other components. So you just intersect with all the other components. So it's something like minus gamma intersected by k, where k is different from I, if I is j.
So you just multiply by the first Chern class of the normal bundle, and it is equal to minus some of the other components, right?
Okay, that's a way of saying, yes. But then you need to know, well, no, I think that is fine, yes. As long as you agree that this is a statement only about the special fiber, that has nothing to do with the total space. So it's just a statement about the special fiber and about 1 cycles and 0 cycles on this thing. And if the generic fiber is CH not universally trivial, then the special fiber has to have the property that this funny map that I wrote down is always surjective. Okay, and then what you can do is you can write down some degeneration, look at the special fiber, and try to find a 1 cycle in here, maybe after some base change, that has degree 0, but it's not hit by that map. Now the issue here is that this only says something about the generic fiber, and we would be interested in the geometric generic fiber. So for this one has to work a little bit more. So if the geometric generic fiber is universally CH not trivial, and then I need to assume that the special fiber is a chain of components. So the dual graph is really a line. So it looks like this. So there's one component, another component, and so on. Yeah, so the simplest non-trivial case that you can imagine. And if we are in that simple case, then we can then we still get a statement on X, and we get that for every unramified extension of DVRs, this map from above applied to the base change of curly X is surjective modulo 2. Okay, so what's the point about 2? Well, in practice, if we have some nice degenerations like the one of Nikkei, we would like to apply this. Well, but I don't want to say that the generic fiber is not stably rational or has no decomposition of the diagonal, because that is a variety over a non-closed field. I want to say this over the geometric generic fiber. One way of doing this is to do a base change, but then I have no control on the base change. And after resolving the singularities, the special fiber will have a lot of components. And then it's difficult to compute this map because there will be a lot of components. In theory possible, but difficult. 2 has an advantage because if I write down one model with very few components in the special fiber, this map here is easy to compute. I have few components. Nonetheless, I can make an assertion about what happens on the geometric generic fiber. So what happens about base change. The price I have to pay is that I only get surjectivity modulo 2 and not surjectivity on the nose. However, the way we will apply this theorem, we will apply 2, and we will find a degeneration with 3 components where I think 3, yes, that is similar to the Nikkei degeneration, where after some unramified extension of DVRs, we find a 0 cycle in here that has degree 0, but cannot come from here. So that's how we prove the following theorem. So we apply 2 of the theorem to a degeneration similar to Nikkei's autumn to get the following theorem. So the characteristic of the field should not be 2, and X is a very general quartic. Then X has no decomposition of the diagonal, equivalently is not universally CH not trivial, and hence X is not retract rational. And the remark is that if the characteristic was positive, then rationality was open for these varieties. Okay, so I think I'm already over time. So let me stop with one more remark here. So there are two remarks. So yes, I don't have time to prove that theorem, but two follows from one by looking at what base changes do. So the main point is one, and one is in fact a surprisingly simple statement, but it took us quite some time to realize that such a thing exists. Well, that this is the correct thing to look at. So that one has to look at these one cycles. But it does not have a difficult proof. So the proof is quite simple. I could show it in 5 minutes. But then to apply it, this is really a lot of work, because so the Nicaise-Ottem example on the nose doesn't work. So we need to look at some variant that depends on a lot of parameters, and we need to do a lot of degenerations to control the situation. And the main issue is that if you want to apply such a map, okay, so maybe you know something about CH0 of the components, and you find an interesting zero cycle here. But the problem is that you need to control it does not come from CHA1. So you need to know CHA1 of these components, and that's difficult. So computing CHA groups of varieties in general, very difficult, and in particular, CHA1. So the only way we can control this is that we include a lot of degenerations that make our components simpler and simpler, so that we can control better the CHA1. So this is a technically, unfortunately, not so nice and not so simple, but it works. Okay, I stop here. Sorry for going over time.
Thank you. Any questions?
Can you explain which degeneration do you consider? You said it's similar to Nicaise-Ottem, but
It's very similar. The only problem is that you need to. So in Nicaise-Ottem, well, the picture is the same. Where is this degeneration?
Yeah, it's here.
Here. Okay, so one difference is that F here was quite arbitrary, apart from some symmetry conditions. We don't care about symmetry conditions, but our F has to have certain degenerations, and yeah. So this part is technically demanding. I'm not sure I would even be able to write down the correct equation now out of the top of my head. And then also this on the nose is not the correct thing to do, because so one also has to change this one, and that's because in the whole discussion I neglected the singularities you get. So that total space is actually not strictly semi-stable. You need to blow up something, and that also causes problems. You know, these are small blowups. So a small blowup doesn't change the stable birational equivalence type of the components, but it does change the CHA1. So we need to take care of this. So it's essentially the same thing, but different. Sorry.
And
a little bit different, yeah, but very similar. So for instance, the components they should have degeneration, so that they are smooth, but they allow degenerations to something that has a triple point, so that it is rational, and you can then use a rational parametrization. You know, you realize it as a blow up of P something to compute its CHA1. That's one important step. And then yes, okay. So I think to simplify manner, we actually keep the symmetry between Z5 and Z6, even though it's not so essential. But we keep that trick from Nicaise-Ottem just to simplify computation. And then there is one more technical subtlety that one has to change this equation a little bit to keep track of what you introduce by these small blowups. So so I think that's all.
But do you at least keep it quadric?
Yeah. So it's essentially that example. You just manipulate it a little bit. But,
so you increase the rank of the quadric slightly, right? Do you?
Well, where is the quadric? This one?
Yeah.
Yes, yes, I think so. Yeah.
Okay. Thank you.
So in Y,
Yes. Where should I scroll? Here?
so may I ask, why was characteristic 0 crucial for, in any case, quantum?
Yes, so that result is really, you look at the two total spaces. So you assume the generic fiber is rational. That means the total space is birational or stably birational, but you can reduce to being rational to the trivial PN family. Okay, so you have this rational map, and then you use weak factorization. You blow up, blow down, blow up, blow down.
So just to reinterpret the quantum model. Yeah. So
and then you just keep track of this formula that I wrote down in each step, and you see it doesn't change. And so at the end of the day, you need to get a point because that's what you get on the right hand side.
Weak factorization is.
But so it's weak factorization is very central to this. So if you don't have resolution of singularities, that is not going to work.
Mm-hmm. And a philosophical question. So this possible example to retract rationality being different from stable rationality failed. And so what do you actually expect in this direction?
Well, I'm pretty sure that they are different. You know, all these notions are different, but it's difficult. I don't know. I mean, the problem is, okay, so for sure so my feeling would be that this motivic obstruction could in fact be sensible to stable rationality. You know, it could be the right tool to detect something that is stably rational, but not retract rational. But what I don't know how to do is how to construct an interesting variety that is retract rational. Mm-hmm. That's okay. I mean, one possibility would be a variety that becomes rational after product with something that is not projective space. But also that is it's a completely open question whether something like that can happen.
Mm-hmm. I see.
But I wouldn't be surprised if that motivic obstruction at some point will actually lead to a counterexample.
You mean becomes rational after a product with something which is itself not stably rational?
Yes, exactly.
Yeah. But how about low dimensions? For example, surface over non-closed field. Is it maybe more clear? No?
Oh, that's a good question. I don't know if people looked at this. I haven't thought about it, so I probably can't answer out of the top of my head, but this might be feasible. I mean, it sits in between unirationality and stable rationality. So, yeah, I don't know. I would guess that one can answer it for surfaces, but I don't know.